Hello. Hello, everyone. Come on in. I didn't come as early as I normally do, but still got a little bit of time, so ask me questions if you have them. You can also chat me your first and last name, as James has already done. Still got about 2 minutes. As I said earlier, you're allowed to ask me questions now if you have any. You can also go ahead and chat me your first and last name for attendance. Doesn't matter if y'all end up leaving early or anything like that. I don't count attendance in such a way that you would lose any kind of points or mess up your grade by not attending. But you would mess it up unintentionally or indirectly by just missing the material and that sort of thing. But feel free to ask me any questions you might have, and do chat me your first and last name. Thomas, I think I saw that you had sent me a reply email to my reply. So I didn't get a chance to read it. I just saw it the second I went to log in. So I'll be replying to that soon. We have about 1 minute left. I will be using our e-textbook to go through various examples. However, I've actually taken the time to type them up in a slightly different format. Hopefully, that's enough to avoid any problems with copyright. Either way, it might not be, I don't know, but I'm sure it'll take a long time for them to get to me because it's not like I'm making any money, so they won't care. So, anyways, the first several examples I've typed up, but eventually I'll get to examples that I haven't typed up, at which time I'll be reading them to you from the e-text. So if you can look at your e-text or have it open, that would be extremely helpful for you specifically because I'll read it thoroughly. I'll probably read it more than once and that sort of thing. But if you need more out of it than me reading it the one or two times I read it, then you'll need to be able to read it yourself. All right. We now have 13 students in here. That's a little smaller than the number that's enrolled, so I would prefer more, but that's okay. We're going to go ahead and get started. I'm wearing my Monday shirt with my minion on it. Woohoo! It's an old shirt. I got to get a new one because the ink is starting to crack up. But I'm a aficionado of goofy cartoon related t-shirts. So that, and I follow some people on Twitter, and they always do are on TikTok and Instagram. They do various shout outs for the shirts they wear. So I don't know. I just got a hair or a hair at my butt and made me think. I don't know why I said that metaphor, but anyways, I just decided on a whim to tell you my shirt. I don't know why. All right, so let's go ahead and get started, folks. When we last met, we had gotten up through discussing average velocity versus average speed and stuff like that. We're going to finish that talk today by talking about acceleration, and what we're coming up with is a series of kinematic equations. And I'll sort of recap that to some extent, but these are the equations you're going to be using. And additionally, we're going to ultimately get to a point where we could derive kinematic equations that have acceleration that's not a constant. So the kinematic equations that we work out in this chapter, and I'll derive them for you, those are going to be kinematic equations that require the acceleration to be a constant. But then, if time permits, I'm going to do a derivation of a set of kinematic equations, or at least a shortened version of the kinematic equations for the event that the acceleration is an actual function of time. The big deal is there's a process that you go through in deriving it for a constant acceleration, and that process is exactly the same whether the acceleration is a constant or not. So let's go ahead and get started. I'm going to begin by sharing my screen with you, and you'll see that I think this is it. Hopefully this will work. Okay, so you can see that I have two problems written up on here already. Example 2.5, a car accelerates from rest to 90 kilometers per hour. By the way, that's 90 kilometers per hour is about 55 miles per hour. It also happens to be 25 meters per second, so that makes it work a little better. So it's like 55. Uh, but anyways, a car accelerates from rest to 90 kilometers per hour along a straight road in 5 seconds. What is its average acceleration? So the equation that I alluded to last time is that just like velocity, the average velocity specifically is a change in position. In other words, you calculate what we call the displacement, and the displacement is a vector that refers to not only the distance but also the direction of your change in position. Okay, and then you divide that by the time taken, and that gives you the average velocity. The instantaneous velocity was done by doing the same quantity, but taking the limit as the time interval went to zero, and that converted it from a type slope type formula to a derivative. And that's what we're doing here is we're going to say the acceleration is a slope type calculation, the average acceleration is, where it's a change in velocity divided by time taken. And then the instantaneous acceleration will be the same quantity, only taking the limit as delta t approaches zero. So with that in mind, I'll write out that we have solution A bar is equal to V final minus V initial over T final minus T initial. And there's a lot of different ways to write that. Sometimes I'll write no subscripts on the V final or the T final, and then I'll just write a subscript of 1 on the initial or a subscript of 0 on the initial. That's another way. I also sometimes will just say delta V over delta T, and sometimes I'll just call that delta T just plain T because it doesn't really matter too much. What we do know is that the car accelerates from rest, so that tells us that V initial is equal to 0 meters per second. We also know the final velocity was 90 kilometers per hour, which if you convert, I think you'll see that it turns out to be 25 meters per second. And then delta T, actually, I shouldn't have tried to fit it in there. Delta T is going to be 5.0 seconds. And we want to know A bar equals question mark. So A bar is equal to V final minus V initial. That is 25 meters per second minus 0 meters per second divided by 5.0 seconds. I want you to notice how much this is like a typical statistic that hopefully y'all have all at least read or heard about before. But it's specifically the most specific way of telling a potential car buyer, say, or someone interested just in the car in general, exactly what its acceleration is. So if you've heard it before, this will sound familiar. If you haven't, then commit it to memory because this is a good way of keeping track of how we define the average acceleration and therefore the instantaneous acceleration. Specifically, if you go to a car dealership, and you ask them how good is the acceleration, they might tell you the 0 to 60 time. And what that means is how long in seconds does it take for the car to go from 0 miles per hour to 60 miles per hour. Back before we had the Tesla Plaid, uh, really good, fast, accelerating cars like the Mustang or the Trans Am or something like that might have went from 0 to 60 in 4.0 seconds, and that's a really good one that I used to use because it'd be 60 miles per hour minus 0 miles per hour divided by 4.0 seconds. And if you divide 60 by 4, you get 15. So it turns out to be 15 miles per hour per second. But that is a measure of the acceleration directly. Other things that people might specify would be the horsepower or the horsepower to weight ratio, stuff like that. But those are less direct statements of acceleration, whereas the 0 to 60 is a usable definition, and it matches what we know of as our formula for acceleration. You're thinking a change in velocity divided by a change in time. So in this case, we get 25 meters per second divided by 5 seconds gives you 5.0 meters per second every second. Now, it's perfectly fine to write that as meters per second squared, like I wrote it there, but you really want to express that as meters per second every second or meters per second, because that physically means something. What we mean by this is if this vehicle actually had a constant acceleration, then you could expect at 0 seconds to be going 0 meters per second. After 1 second, it'll be going 5 meters per second. After 2 seconds, it'll be going 10 meters per second. After 3 seconds, it'll be going 15 meters per second. After four, it'll be going 20 meters per second. And then after five, it'll be going 25 meters per second. Notice how the change in velocity was the same for each second. That's what Galileo defined as constant acceleration. The change in velocity is a constant for a given interval of time. Just like in the case of the Mustang, I told you 0 to 60 in 4.0 seconds, that would be 15 miles per hour per second. So we're seeing that the velocity will change by 15 miles per hour each second. Just like this one says, the velocity will change by 5 meters per second each second. Any questions on that? Okay. Now we have a conceptual example, and I don't always do those. I want to remind you, though, that when you run across one, you definitely need to do them. The conceptual examples are a lot of times the most important examples in the textbook so that you can better understand certain nuances of the stuff. So even if I don't cover them, I want you to cover them. And when I do cover them, I rarely actually work out the stuff. I sort of just explain it to you in words. So you'll have them in video form, but probably the written form that the author gives you is a little better. In this case, it says if an object has a velocity of 0, does it have an acceleration of 0? Part B, it says if an object has an acceleration of 0, does that mean its velocity is 0? So let's take this first one first. If an object has a velocity of 0, does it have to have an acceleration of 0? Well, acceleration is a change in velocity divided by time. So the fact that it has a velocity of 0 doesn't mean it's always going to be 0. It just says it currently has a velocity of 0. And the formula for average acceleration, you can tell, is v final minus v initial. So you need two different velocities. Now, if it was the velocity 0, and then you wait a little while and the velocity is still 0, and you wait a little while and the velocity is still 0, then yes, the acceleration would be 0. But just like when I throw an object up. I wish I wouldn't have done that because I forgot I can't look at it too well. But when I throw an object up, it reaches the peak of its motion. It comes to a stop. We know for a fact, you might not know this yet, but you will know it after chapter 3 and after the end of this chapter. But at a split instant, at the very top of the motion, the velocity is 0. But if you turn the clock back 1/10 of a second, the velocity would be positive because it's going in the upward direction, and we'll assume up is positive. Or if you go a split second forward in time, 0.1 second, for instance, it'll be going in the negative direction. So it'd be a negative velocity. The important point being that in between those, the velocity was zero, but the acceleration at all of that time was negative, meaning downward, 9.8 meters per second every second. So keep that in mind. So in this case, where it says if an object has a velocity of zero, does it have to have an acceleration of zero? It does not, unless the velocity is zero, and the velocity is still zero, and the velocity is still zero, and the velocity is still zero. Okay. Part B, it says if an object has an acceleration of zero, does it mean its velocity is zero? An acceleration of zero could be sort of well, it could be the case where the velocity is zero. If I look at my car sitting out there in the driveway, I know the velocity is zero, and I also know that if I sat in it, my head wouldn't jerk one way or the other. And our heads are really good like that as detectors of acceleration. They do not detect velocity, and we'll learn that as the semester progresses. But the main thing is when you feel that urge for your head to flip back or left or right, that's a indicator that you're actually experiencing acceleration. So if I go out there and sit in my car and don't feel my head move at all, then chances are there's no acceleration. And then I look at the speedometer and I see, oh, well, yeah, of course, it's just sitting perfectly still. And I look at the trees around me and they're not moving either. So in that case, we know that the acceleration being zero happened to correspond with the velocity being zero. But I could also just drive out on the road, assuming my cruise control is perfect. I could click on the cruise control at 60 miles per hour. And if the cruise control really is perfect and the road is really straight and not downhill or uphill, then we would be pretty confident that the acceleration in that case is zero because the velocities meet reading a constant, let's say 60 miles per hour and then 60 miles per hour and then 60 miles per hour. Any questions on that? So this one was just explained in words. Hopefully that helps you. Let's go on to example two.
So, real quick, just to
Yes.
make sure we're clear. So, you're
Mhm.
saying that acceleration and velocity don't actually have to be like a ratio for any means. But so, my question would really be if acceleration was zero, does that mean velocity has to stay at zero?
No, that's exactly the opposite of what we've found. We found that there is cases where the velocity being zero could make zero acceleration, or where the acceleration being zero could make zero velocity, but that is not necessarily the case. It can be zero velocity with a positive or non-zero acceleration. It can also be zero acceleration with a non-zero velocity.
Okay, that makes sense. Thank you.
No problem. I hope it did because it was a real mouthful when I said it, and I was thinking, "Oh crap, that was probably the worst bout of teaching I've ever done." So, please feel free to ask me to follow up if you don't understand it. So, here's example 2.7. A car is moving eastward along a straight interstate road. Then the driver puts on the brakes, and the velocity changes from 15 meters per second to 5 meters per second in 5 seconds. If we assume the positive x axis points eastward, what is the car's average acceleration? And then the second part, what if we considered the westward direction of the positive x-axis? So that's what we're shooting for here. So I'm going to write down the information I have. So what I have is the velocity changes from 15 meters per second. So I'm going to say that's V1 equals 15.0 meters per second. And remember, 15.0 meters per second in a science world is different than 15 meters per second, and that's different from 15.00 meters per second. Uh, it's going to go to a final speed of V2 equals 5.0 meters per second, and the time over which that happens we'll call delta t, but I could also just call it t, or I could call it t2 minus t1. Any of those are all acceptable. That time is 5.0 seconds. Again, the 5.0 being different from just 5 seconds or just different from 5.00 seconds. And what we want to know in part A is the average acceleration. And then in part B, we want to know the average acceleration too. But that case is with uh, going in negative direction. I know that's not a really good sentence, but I was just trying to speak off the cuff and give you an idea of that. So our solution here is going to just involve the equation for the average velocity, which is v final minus v initial over t final minus t initial, which is also equal to delta v over delta t. So for part A, the average velocity. Since we're going in the eastward direction, that means for part A, the velocity initially is 15 meters per second in the positive direction, and the final velocity is 5 meters per second in the in the positive direction as well. So I'm going to write positive 5.0 meters per second minus positive 15.0 meters per second, and that took a time of 5.0 seconds. In this case, we get 5 meters per second minus 15 meters per second is negative 10 meters per second. So that's negative 10.0 meters per second. Notice how that is the correct answer, even taking into account significant figures. And then that is divided by 5.0 seconds. And that result, of course, is negative 2.0 meters per second per second. So the acceleration in this case is negative 2.0 meters per second. Hmm. All of a sudden, my red pen just started acting like it don't write. That's weird because it's electronic. All right, now let's look at part B. The difference being we're sort of looking at part A as if this direction is the positive direction, and now we're looking at part B as if this is the positive direction. So in this case, the acceleration is going to be negative 5.0 meters per second minus negative 15.0 meters per second. Notice the difference is now they're traveling in the negative direction because eastward is the negative direction and westward for this part is the positive direction. And these vehicle was traveling in the eastward direction and initially and finally. It's still divided by 5.0 seconds, but in this case we get negative 5 minus a negative, which means plus a positive. So it's literally 15 minus 5, which would be positive 10.0 meters per second. Notice again that the sig figs are correct for this. And in this case, we get positive 2.0 meters per second every second. And I'm choosing to write the meters with the exponent of the meters per second every second with the exponent of 2 on the seconds, just because it's so much harder to write meters divided by seconds. Okay. So the main reason I did this example is students often think that a negative acceleration means that the object is slowing down, and obviously sometimes it does because that's what happened here in part A. In part B, it was still slowing down, but in this case, we got a positive acceleration. So I just wanted you to realize that a negative acceleration can also come from an object speeding up. For instance, if we had chosen an object speeding up in the negative direction, then we would have gotten a negative acceleration. So let me just give you that one. So consider V final is going to be negative 15.0 meters per second, and V initial, which is also going in the negative direction, is going to be negative 5.0 meters per second. And let's say delta t is still 5.0 seconds. So in this case, the average acceleration, which is, as you know, v final minus v initial divided by delta t, in this case, it's going to be negative 15.0 meters per second minus negative 5.0 meters per second divided by 5.0 seconds. Now, negative 15 minus negative 5 is the same thing as negative 15 plus 5. So that's negative 10.0 meters per second divided by 5.0 seconds. And that gives me negative 2.0 meters per second every second. And that's what I meant by writing it the way that's a little more difficult to write. So this is an example that was speeding up, yet a is less than zero. So just know that the acceleration being a negative number does not imply slowing down, nor does the acceleration being positive imply that it's speeding up. Anybody have any questions on that? I did ask everyone to chat me your first and last name, so if you guys haven't done that yet, by all means, go ahead. We're going to press on here. Anybody have any questions before I move on from that example? All right, well, let's move along then. So it says a car is found to have a position x of t given by x of t equals 2.10 meters per second times t squared. That 2 was supposed to be an exponent, and I thought I made an exponent before I copied it in here, but it looks like it did not make an exponent, so I apologize for that, but that's what's supposed to be there, plus 2.80 meters. So a car is found to have a position x of t given by 2.10 meters per second times t squared plus 2.80 meters. A, what is the velocity as a function of time, v of t? Recall, in one dimension, a vector quantity's direction is indicated by the sign being positive or negative. B, what is the acceleration during the time interval between 3 seconds and 5 seconds? And then C, what is the car's instantaneous acceleration as a function of time? So we're going to work on that now. So what we've been given in this case is x of t is equal to 2.10 meters per second every second times t squared plus 2.80 meters. Put that in parentheses just so it's a little cleaner. And what we want to know is part A, we want V of t is equal to question mark. Part B, we want the average acceleration, so A bar from t equals 3.00 seconds to t equals 5.00 seconds. And then in part C, we want to know the car's instantaneous acceleration. So we want to know A of t instantaneous. So I can just write that INST there. Now, solution requires us to state some things that we know. So for instance, one of the things we know is that V of t is equal to dx dt. Another thing we know is A bar is equal to V final minus V initial over T final minus T initial. And then finally, another thing we know is A instantaneous is equal to dV dt, which is also equal to d2x over dt squared. And again, remember it's delta v over delta t is the average velocity, or excuse me, average acceleration. And if you want the instantaneous, just like you learned in Calc 1, you take the limit of that quantity as delta t approaches zero, and that makes the delta v over delta t become a derivative, just like we did when we went from average velocity to instantaneous velocity. So let's begin. So for part A, we are asked specifically for the velocity as a function of time, and the velocity as a function of time is d by dt of x of t, which we can see is The derivative of 2.10 meters per second squared times t squared is 2 times 2.10 meters per second squared times t. And then the derivative of the 2.80 meters is just 0. So this is going to be 4.20 meters per second every second times t. That is the actual velocity as a function of time. So I'm just going to write that here. V of t is equal to 4.20 meters per second times t. So there's our answer to part A. Part B, I need A bar, which equals V specifically of 5.00 seconds minus V specifically of 3.00 seconds. And all that would be divided by 5.00 seconds minus 3.00 seconds. Now, if we look at V of 5 seconds or V of t, what we see is whatever the time is, it's going to be multiplied by the 4.20. So if I multiply 4.20 times 5.00, the 5 times the 4 gives me 20, and then the 5 times the point 0.2 gives me just plain 1. So that'd be 21.0 meters per second. Notice the fact that the time is in seconds and is being multiplied by the meters per second cancels out one of the seconds and gives us the units that we expect for velocity. So that's the V of 5 seconds. Now the V of 3 seconds is going to be 3 times 4.20. Well, I know 3 times 4 is 12, but then 3 times zero point 0.2 is zero point 0.6, so this should be 12.6 meters per second for that. And then, of course, 5 seconds minus 3 seconds is 2.00 seconds. Now, 21 minus 13 is actually 8 meters per second. So 21 minus 12.6 would be 8.4 meters per second. So this is going to be 8.4 meters per second divided by 2.00 seconds. So A average is in fact equal to 4.2 meters per second per second. Anybody have any questions there?
When you substituted for V, you used 4.20?
Yes. Let me go ahead and explain that a little better because I was afraid by showing that that might have made it a little less obvious. So V of 5.00 seconds literally means 4.20 meters per second times 5.00 seconds.
And that's
Because
because we're substituting with the answer we got in part A.
exactly. Yep.
Thank you.
No problem. And you can see that that 12.6 came from doing the same thing but putting a 3 there. Does that make sense, Jaden? I think that was Jaden that was speaking.
Yes, it does. Yes,
Okay.
it's me.
Cool. Yeah, and yeah, do ask these questions. These are really good. And even if you think they're quote unquote dumb questions, trust me, if you've got it, 6 or 7 other students in the class has it too. So please, by all means, keep asking questions. That's excellent. Anybody else have any questions on that part?
And then, sorry, I don't mean to backtrack.
No
Um,
problem.
for part A,
hmm
um, how do you end up with 4.2? With
So the derivative of, let's say, t squared would just be 2t, but we have instead 2.10 t squared. So when we take the derivative of that, that becomes 2 times 2.10 times t.
I got you.
That makes sense? And it is kind of weird. We're not used to using units in our calculus. So it is particularly odd when I do that here. So I get you. All right, well, let's move on to part C. And part C is asking for the instantaneous acceleration as a function of time. And that just means taking the derivative of v as a function of time. So for part C, v of t is equal to, or excuse me, everything about that was wrong. A of t is equal to dv over dt, which is d by dt of, oops, that's right, 4.20 meters per second every second times t. That's what we're taking the derivative of. You can see this is like linear. So like y equals mx, the derivative of that is just m. So similarly, the derivative of this is just 4.20 meters per second every second. And that is the A instantaneous. And it's technically also the acceleration as a function of time, only it isn't really a quote unquote function of time, it's a constant. Okay? Any questions on that? It's still okay to call it as a function of time. It just happens to be that the time dependence is nil. Anyone have anything on that one? Okay. So we've now sort of exhausted all of our examples regarding average acceleration, instantaneous acceleration. These are more or less like the ones that the book did, but now we need to go on a little further and talk about the general case of acceleration being a constant and the resulting equations. So I'm going to go ahead and do that. I'm going to start off by letting you know some of the things we already know as our kinematic equations. So our kinematic equations include the average speed is distance traveled divided by time taken. So I just write that like that. We also know our average velocity is equal to v final minus v, or excuse me, I slipped into acceleration mode. It's equal to x final minus x initial divided by t final minus t initial, which can also be written as delta x over delta t. So that's another one of the kinematic equations. We also found that the average acceleration, A, is equal to v final minus v initial divided by t final minus t initial, which we can also write as delta v over delta t. So maybe we'll call this equation 1, we'll call this equation 2, we'll call this equation 3. We'll go on though and remember that our instantaneous velocity is equal to dx over dt. So this is going to be equation 4. And our instantaneous acceleration, A instantaneous, is equal to dv dt, which is equal to d2x over dt squared, just in case you were a little rusty on remembering the terminology and the symbology that we use when expressing a second order derivative. So these are what we know to date. Now I'm going to say consider constant acceleration. A of t equals A, which is a constant. So that's what we're working with here. So I'm going to start off using equation 5. Okay. What we know is A is equal to dv dt, and A is a constant. Now, this is what we call a first order differential equation. Okay, it's really one of the simple types. It's what we call a separable differential equation, and it's more or less trivial to solve. What I'm going to do is I'm going to multiply both sides by dt. So I'll write this in a different color so you can see the individual steps. So I'm multiplying by dt, but whatever I do to one side, I got to do to the other. Remember, that's sort of the rule with equations. Other than multiplying through by zero or dividing both sides by zero, you can do anything you want to an equation as long as you do it to both sides. Now that I have it written this way, I'm also going to integrate both sides. So that's why I wrote it in purple for the second step and red for the third step, so you can see that there's three different steps there. Hopefully that was helpful for you. Now, I also would like you to notice that the right-hand side, that is basically just a representation of part of the fundamental theorem of calculus. The fundamental theorem of calculus is that by some happenstance, the weird method that we used or had to invent, or Newton had to invent to find the instantaneous rate of change or the slope of the tangent line of a function, i.e., the derivative, that happened to be exactly the opposite operation as the process that Newton had to invent to find the area under a curve. There was no reason why the area under the curve had to take the opposite operation for finding the slope of the curve, but it did. And the fundamental theorem of calculus therefore says the integral of a derivative, just like the derivative of an integral, is the original function. So in this case, what we're going to get is the integral of a dt is a times the integral of dt, but notice we're integrating it without limits of integration. So what do I have to do on the left-hand side? Can anybody tell me what the left-hand side will be equal to?
Acceleration multiplied by time.
Exactly. But what else do we have to do since there was no limit of integration there? Jaden, do you know?
I I
You probably
don't.
remember it's just your you might be thinking it's more complex than it is. When you integrate without limits of integration, you have to add a constant, an arbitrary constant. Remember that? So we're going to say plus c. So the AT was right. You actually did the calculus part right, but remember, if we don't put the limits of integration on, then it could be that AT plus any arbitrary constant. Because notice, if you take the derivative of AT, you get A. If you take the derivative of AT plus C, you get A. You take the derivative of AT plus C2, you get A. So any arbitrary constant could be added to it, and that's the reason why you have to add the arbitrary constant. Now the other side is just going to be V, and now even if you haven't had differential equation, you will learn that evidently a first order differential equation, and that's a differential equation that has only a first order derivative in it, a first order differential equation requires us to have one initial condition. A second order one, which would be like a second derivative, has to be in the equation somewhere. That has to give you two initial conditions. So you can't just solve a differential equation without having some initial conditions. If it's the first order, you have to have one initial condition. If it's a second order, you have to have two. If it's the third order, you have to have three, and so on and so forth. But I think you can see that is exactly a ramification of the number of integration constants you get. So now I'm going to say assume v of 0 is equal to v0. All right, let's write it a more general way. I'm going to say assume v of t equals v0 at t equals 0. So that's what we call an initial condition. It's initial condition because it's happening at t equals 0. But to be honest with you, you don't really have to have a quote unquote initial condition. You just have to have some condition that allows you to evaluate, for instance, this constant c. In this case, that means a times 0 plus c has got to equal v0, and that means that c is going to equal v0. Does everybody follow what I just did there? Now, this process I'm going through is exactly the same process that you do if you're trying to derive the kinematic equations like I am now, but it's also the same that we do if I said you have to find the kinematic equations when the acceleration is not a constant. If the acceleration is not a constant, the only difference would be you'd have a function in that left integral in place of a. Instead of a being a constant, you'd have some function like 3t squared plus 2t or something, right? That's the only difference. And then you'd have to have an initial condition. It might even be the exact same initial condition that v of t equals v0 when t is equal to 0. Now that we have that, we can now apply equation 4. And by the way, we're going to say this result is that v of t, which is just plain v that we solved for before, that's equal to at plus v0. I think if you look at that, you'll realize that this equation is exactly the same as the average acceleration equation, equation 3. Okay, except equation 3 was for finding the average acceleration. This is the equation for velocity as a function of time, assuming the acceleration is a constant. So now that we have that, we can go ahead and use equation 3, or excuse me,
Can you say that
equation
last part
4.
again, please? You
Yes.
said that it's a function of
So,
velocity at, go
yeah,
ahead.
the v of t, this equals at plus v0. That is the velocity as a function of time if the acceleration a is a constant. Whereas equation 3 was the definition of average acceleration, a bar equals v final minus v initial over t final minus t initial. If you just made t initial be 0, because you can always call the initial time 0, just like you can always call the initial position x0 equals 0, you can do that here and you'd see that you'd end up getting a bar t equals v final minus v initial, so that v final would equal a bar t plus v0. That's exactly the same as the equation I have written there in that last line. Does that make sense, Jaden?
Yes, it does. Thank you.
No problem. All right, now that we have that, we can go ahead and apply what I said was equation 3, but I meant equation 4. So now we can say 4 at plus v0, leaving a bit of a space, is equal to dx over dt. See how I used equation 4? It says the velocity, instantaneous, which is the same thing as the velocity as a function of time, is equal to dx dt. This is a first order differential equation. Therefore, what I'm going to do is multiply both sides by dt. And to make that clean, I'm going to put it in parentheses. And now the next step is I'm going to integrate both sides. Okay. Now, the left-hand side's a little more complex, but remember, I don't have limits of integration, so I've got to add another constant to it. We would normally call it like C2 or something like that, but we know we're going to get rid of it, so I'll just call it C because I've already got rid of the C before. But the left-hand side, you guys try to predict what the integral is before I write it down, and then check yourself when I do write down the result. So the result is... And then the right-hand side, remember, is again just a restatement of the fundamental theorem of calculus. So in this case, it's just going to be equal to C. Now we're going to say, assume x of t is equal to x0 at t equals 0. If that's the case, then what we get, x of 0 is equal to x0, but that's equal to, in this case, 1 half a times 0 squared plus v0 times 0 plus c. Therefore, you see that c is just going to become x0. So we have another result. We can say x of t, which we'll never write it that way. We'll almost always just call it x, is equal to 1 half a t squared plus v0t plus x0. And this is another kinematic equation. And this would be called, for instance, equation 6. This is just like equation 3, but a bar equals a constant. So that's why I didn't choose to number that equation, because we already had a form of that equation, just the difference being a bar was used instead of just plain a, since a was a constant. But we now have a kinematic equation, a new one, and we technically have a second kinematic equation. The v equals at plus v0 is another version of equation 3, but it's a whole nother equation as well. So what I'm going to tell you is we have a couple more equations that we'd like to have. But one of them is, what if you wanted to know like the final velocity or the initial velocity or the acceleration or something like that, but you didn't have a time variable? So the way we can address that is I'm going to solve, let's call this quantity, this equation right here, I'm going to call that 3 prime. So I'm going to solve 3 prime for t and plug that into equation 6. Okay, because it'll give us another kinematic equation. Now, I'll tell you, this result that we're going to come out with will end up being a non-vector equation. So there's literally, tons of professors all over the United States or all over the planet, for instance, that sometimes will teach this entire course and never give you the equation we're getting ready to have. So just be advised that future teachers might not let you use this equation. So I'm going to start it this way. First off, I'm solving 3 prime for t. 3 prime gives me t is equal to v minus v0 over a. Notice I'm not using the phrase vf. I'm just using v for the final velocity, and I'm using v0, not vi, for the initial velocity. But that's that. Now I'm going to plug this into equation 6. So I'm going to get x. Well, actually, let's start it with, I like writing in blue. So I'm going to say x is equal to 1 half a t squared. So that means v minus v0 over a quantity squared plus v0 times t, which would be v minus v0 over a plus x0. Now, it turns out that this equation is a lot easier to work with if I put the x and the x0 on the same side. So I'm going to say x minus x0 is equal to 1 half a. Now I'm going to go ahead and square that binomial inside the parentheses there. So that's a skill you need to know. So the way it works is you square the first term, and then you take 2 times the product of the two terms, so that'd be minus 2v v0, and then you add to it the square of the second term, so that'd be v0 squared. Now the denominator is squared as well, so that becomes a squared, and you can see that the exponent of 2 cancels out with the a here, and in fact that 2 is going to become a denominator. So that's something that we're going to make use of in a second, but I need to now distribute the v0 in the numerator of the second term. So this time I get v0 minus v0 squared. And then, of course, the a is in the bottom. But we saw that we have a denominator of 2a. So it would be nice to get a common denominator. And the way we do that is we multiply the numerator and the denominator by 2 over 2. Okay, so you're actually multiplying the numerator by 2 and the denominator by 2, but it's 2 over 2, so it's 1, so you're not changing anything. Now, because of that, we'll now have a common denominator, and we can say that, for instance, we have v squared minus 2v v0 plus v0 squared. Now I've got to remember to distribute this 2, so I'm going to say plus 2v v0 minus 2v0 squared. All of that is going to be over 2a. So I know I wrote that kind of small, but can everybody follow what I did there?
What about the x zero?
I pulled that to the left-hand side already in the first step.
Oh, okay.
You see it there? But yeah, that's a good thing to watch out for. Anybody else have any questions about this? So you might see that we have two pairs of like terms. So for instance, this negative 2v v0 and this positive 2v0, or excuse me, positive 2v v0, those two are equal but opposite, so they're going to cancel out. And then these two, v0 squared minus 2v0 squared is just going to make minus v0 squared. So now I'm going to say I have x minus x0 is equal to v squared minus v0 squared over 2a. And to express this in the normal way that it's expressed, I'd say v squared is equal to v0 squared plus 2a x minus x0. That's the other kinematic equation that some instructors don't allow you to use at all, but I do. Okay. Now, for the record, there's another kinematic equation that I found really, really helpful. But I should point out that equation 6, equation 7, and what I called equation 3 prime, if you don't have a bar in equation 3 prime, then it's a distinctly different equation than equation 3. Those three equations are only true if the acceleration is a constant. So 3 prime, 6, and 7 are only true when a is a constant. And this equation I'm giving you now is also only true when a is a constant. And that equation is v bar is equal to v1 plus v2 over 2. So again, this is only true when the acceleration is a constant. Okay, anybody have any questions on that? All right, so that's your kinematic equations, and now what we want to do is show you some examples of how to use this. Anybody have any questions before I move on? Now, if you write these enough, they're going to be stuck in your head, or if you just use them enough by solving enough homework problems, they're going to be stuck in your head. That being said, if you look in the module that says helpful documents and links, you'll see a 242 allowed equation sheet that's going to be on every test that you take that's online or printed. And then you also see Giancoli cover, Giancoli front cover two, Giancoli back cover, periodic table, and moments of inertia. All of those picks will be in your test as well. So these are numbers that you need not memorize because they're all there. Numbers, equations, constants, all that sort of thing. So pay attention to those. And just know that they're going to be on your online test and your face-to-face tests. So let's try an example. You are designing a runway for an airport, and you know the aircraft takes the longest runway must reach a velocity of at least 27.8 meters per second. That's, by the way, 100 kilometers per hour, which is about 60 miles per hour, and has an acceleration of 2.00 meters per second every second. A, is 150-meter runway long enough? And B, if not, what is the shortest runway it can use? So what I'm going to do here is I'm going to say V0 is equal to 0. That's just because we know the airplane is going to sit perfectly still. Then it's going to take off and start accelerating, and it's going to try to reach a final velocity V final equal to 27.8 meters per second. And we know that the acceleration that brings it to that speed will be 2.00 meters per second per second. Okay, so that's the information we know. What we want to know for part A is delta x equal to 150 meters. Is that big enough? Is delta x equals 150 meters big enough? Now, there's a couple of different ways you can do this, but I'm going to show you one way that answers both parts at the same time. And B, if not, how big must it be? So, solution. There's again various ways you could do it. You could, for instance, use equation 3 prime, which was V equals V0 plus AT. That would allow you to calculate, given the acceleration, the initial velocity, and the final velocity, that would allow you to calculate how much time it would take to reach that final velocity. And then you could use equation, what did I call that? 7? No, equation 6, and see how far it traveled according to equation 6 during that time. Or you can do the obvious, which is exactly what we just did symbolically, is we took equation 3 prime and plugged it in 6, and that gave it to us. So that's what I'm going to use instead. I'm going to say v squared is equal to v0 squared plus 2a x minus x0. And remember, this x minus x0 is what I'd normally call delta x. Another way of looking at it is you can always assume the object's initially at the origin, in which case x0 would just be 0. That's the same thing as calling x minus x0 delta x, or you could also just call it plain x. That would be acceptable as well. So in doing it this way, I can plug in all those numbers. I can solve for delta x, and what it's going to give me is the number or the length of the runway that allows the acceleration to happen in the right amount of distance. And if that distance comes up to be greater than 150 meters, then we know 150 meters is not acceptable. And not only that, we already know exactly what is acceptable. So let's work that. So we're going to plug all this in. What we say is V final is 27.8 squared. That's equal to V initial, which is 0 meters per second squared, plus 2 times 2.00 meters per second per second times delta x. So if we square 27.8, if I square that, I get 772.84, which is way more digits than I'm supposed to have. Meters squared per second squared. That's equal to 4.00 meters per second times delta x. Therefore, delta x is supposed to be 772.84 divided by 4. And that gives me 193.21. And if you'll notice, dividing meters squared per second by meters per second gives you just units of meters. And not only that, it's 3 sig figs divided by 3 sig figs. So these last two digits are not significant. So the answer for A is no. 150 is not long enough. Now, the aircraft was unable to reach 27.8 meters per second in 150 meters, and it must reach 27.8 meters per second. So we see that that only happens at 193 meters and some change, and that change would normally be rounded down. But in this case, we need the aircraft to actually reach the full 27.8, so we'd have to automatically round this up, and that means B is 194 meters is the minimum. Now, it's technically the minimum only within the number of sig figs and the placement of the sig figs. If we had more sig figs, we might be able to specify 193.2 meters. Or if we had even more, we might be able to say 190. Oh, actually, you have to say 193.3 meters because it has to make up for the one on the end. But if we had even more sig figs, we might be able to get away with saying 193.21. But either way, I hope that makes some sense. Anybody have any questions on that? All right. Your book does a neat little problem next. It's called Example 211 Estimate. And this is where I haven't typed these up. So I'm going to refer you to your book, and I'm also going to read it to you. So here's example 2-11, and it's an estimate example. It says, suppose you want to design an airbag system that can protect the driver at a speed of 100 kilometers per hour, which is 60 miles per hour, if the car hits a brick wall. So suppose you want to design an airbag system that can protect the driver at a speed of 100 kilometers per hour if the car hits a brick wall. Estimate how fast the airbag must inflate to effectively protect the driver. How does the use of a seatbelt help the driver? So what we have here is V0 is equal to 100 kilometers per hour, which, by the way, I think we already worked that out as 100 kilometers per hour was 27.8. But all I have to do is I need to multiply by 3,600 seconds per hour, no, hours per second. So I got to divide by 3,600, and I got to multiply by 1,000. So it's basically the equivalent of dividing by 3.6. And yeah, that gives me 27.8. So this is 27.8 meters per second. And we want the final velocity because obviously it's going to hit a brick wall. That final velocity is going to have to be 0. And what we want to know is estimate how fast the airbag must deploy. So I'm going to call that delta T is equal to question mark. Now, if you think about a car, what's going to happen is the front end of the car is going to run into the brick wall, and immediately the bumper and the brick wall might not be sufficient enough for you to understand what they mean here. Imagine not just a brick wall, but imagine like a brick dam or a brick fortress wall or something like that, because you want the idea that the wall is not going to give it all, and the car is going to come hit it like this, and immediately the front is going to start to crumble. So you know that is the way they design a car to protect you in a car wreck, is the car crumbles and eats up some of the energy of the collision rather than your body doing it. So really what we want to think about is how far in distance the car can collapse before it gets to the point that it starts to crush your feet or legs or arms or head or anything like that. So what I'm going to say is delta x is on the order of 1.0 meters, because I don't know of any car that has a shorter crumple zone than 1 meter. Every car I've ever seen, from the pedal of your feet where the gas pedals are to the very front edge of the bumper, I've never known of a single car having that. Well, actually, no. I remember the old Volkswagen vans, which were front wheel drive, and you were literally sitting on the very front. Same thing with some of the Mack trucks. I guess they have a really short one, but we're going to assume it's a car, so you have a whole meter to crumple in. Now, we want this thing to accelerate over a distance of delta x. And if I look at this, I can say, well, I've got a delta t, or I want a delta t. I've got a v final and I got a v initial. So I'm immediately thinking the equation that I want to use is that one that I just derived, namely v squared is equal to v0 squared plus 2a delta x. Now, in this case, we're doing it a little backwards in that the final velocity is zero and the initial velocity is the big one. So that's going to be a little weird, but that just means we're going to get a quote unquote negative acceleration unless the delta x is in a negative direction. So with that in mind, we know delta x and we can find a. So I'll solve this for a, and what I'll get is v squared minus v0 squared over 2 delta x is equal to a. So the acceleration, and the reason I'm using this is the acceleration will allow me to figure out uh, a time, because I know that it's going to go from, a certain velocity to zero in a certain amount of time, and I need the time component. This is going to give me the acceleration, and then I can use another equation to get the time. So the acceleration is going to be 0 squared minus 27.8 meters per second squared over 2 times 1.0 meters. So this is 27.8 squared divided by 2, and that gives me 386.42 meters squared, or excuse me, meters per second squared, or meters per second every second is the way that should be said. I really only had two sig figs there, so I'll underline all these. That's the acceleration. Now that I have this acceleration, I can use that to estimate the time by assuming that this acceleration is an average acceleration or that the acceleration is constant. Either one are a pretty good approximation. So if I use the equation A is equal to V minus V0 over T, which is 3/3 prime, that's what equation I'm using, then I can see that T is going to be V minus V0 over A. So the V final is 0. And by the way, this did come out negative, so I should put that in there. Uh, so I'm going to say minus the initial velocity, which is 27.8 meters per second, and then I'm going to divide that by negative 386.42. And it's not going to hurt anything by me using more sig figs than we have. It's a danger if you use the minimal each time, but using a couple extras is not going to be a big deal. So I'm going to take 27.8 and I'm going to divide it by 386.42. Notice the top's negative and the bottom's negative, so the result is going to come out positive, and we'll get 0.0719 seconds. Notice the seconds is exactly the unit we expect from this. We actually have two sig figs, so it's 0.071. So 71 thousandths of a second is how much time uh, we have to make sure the airbag completely deploys. Because if we don't get the airbag there by then your feet are going to start touching the wall. And that's a problem, right? So we definitely want the airbag in place, and we're going to hope your feet are going to readily move backwards with the bending of your knees, not in a backwards way or anything like that. Uh, by the way the airbag works is the airbag spreads the force of your body over a whole airbag, which is in fact quite a bit bigger than the steering wheel, as opposed to just little parts of the steering wheel like this little arm or the shaft coming out or whatever. All that stuff can impale you and further do you harm, whereas the airbag is more of a not necessarily a cushion. It's still very, very hard. And in fact, people have been injured by airbags, but it's still going to spread the force over a larger area so that you have a better chance. And the seatbelt keeps you in line with the airbag so that you don't just slip under the airbag or over the airbag or to the left or to the right. And that could cause a great deal of harm too. So that is the amount of time you have to ignite that whatever mechanism you're going to use to inflate the airbag. Anybody have any questions on that? Okay, so your book goes into talking about how to solve physics problems. I definitely recommend you reading that. I'm going to go ahead and I'm going to skip example 212 and I'm going to go to an example of free fall because free fall motion is part of this section as well, even though we really are going to cover it in the chapter 3 because when we go over projectile motion, we'll have to understand vertical motion as well. So I'm going to go on to that and just let you know that what Galileo discovered after he was put in in-house arrest was that he needed to actually figure out how motion took place. He needed a better understanding of motion in general so that he could understand, for instance, why when the planets actually orbit around the sun, one of the arguments for the Earth not doing that was that if a bird was sitting on a limb and saw a worm and he dropped off the limb to fly down and eat the worm, if that happened and the Earth was moving at some great velocity around the sun, the bird would be left behind. That was their idea because they didn't understand motion as well as we did. They were using Aristotelian laws, and Aristotelian laws would have the bird be left behind. So he decided he needed to understand motion in general to make some sense of that. And he started studying objects going up and down inclined planes, looking at friction forces, trying to reduce them. And ultimately, what he discovered is that all objects fall at the same rate, independent of mass. And that rate is 9.8 meters per second every second. If we round that to 10, it makes it a little easier to explain. Uh, for instance, if we do assume the acceleration is exactly 10 as opposed to 9.8, if I throw a ball up at 20 meters per second, then after 1 second, since the acceleration is 10 meters per second, the ball that you threw up at 20 meters per second after 1 second will be going only 10 meters per second. After 2 seconds is going to be going zero. After 3 seconds is going to be going 10 meters per second downward, which is negative 10 meters per second. And after 4 seconds is going to be going 20 meters per second downward. Notice how the speed changed by exactly negative 10 meters per second every second. So that's the way we did that. Now that we have that, let's look at some individual problems to solve using that quantity. So falling from a tower, example 215. It says, suppose that a ball is dropped from a tower how far will it have fallen after a time of t equals 1.000 seconds, t2 equals 2.00 seconds, and t3 equals 3.00 seconds? Ignore air resistance. So how far will it fall in 1.00 seconds, 2.00 seconds, 3.00 seconds. Now, since we're talking about how far, the solution we'll use requires us to find out how far for a given function of time. So that's x is equal to 1 half a t squared plus v0t plus x0. Now, it fell, and that implies that the initial velocity is 0. So I'm going to write 0 right there. We can always assume that it started from the origin, so we can say x0 is equal to 0. Therefore, we get x is equal to 1 half at squared. That means x is proportional to the square of the time. So if we find how far it will fall after 1 second, then we know after 2 seconds it's going to fall 4 times as far. After 3 seconds, 9 times as far. After 4 seconds, 16 times as, and so on and so forth. Okay? So x at 1.00 seconds is equal to 1 half 9.80 meters per second times 1.00 seconds squared. Now I'm choosing to point downward as the positive direction. That's why I chose to put the 9.8 as a positive. And you're always allowed to do that. The only difference is I'm going to get a distance that's positive because obviously the x-axis points in the downward direction. This answer is 4.90 meters. So that's how far it falls after 1 second. But according to the principle that Galileo discovered, is that the or the distance traveled is proportional to the square of the time. Then at x at 2.00 seconds is x at 1.00 seconds times 4. Okay, because 2 squared is 4. So if I say 4.90 times 2 again, you can see obviously it is 4, and that is in fact 19.6 meters, which means 4 times as big as the other one. And x at 3 seconds is equal to x at 1.00 seconds times 9, because 3 squared is 9. So 4.90 times 9 gives me 44.1. So that's how far it's going to fall in that amount of time. Notice you can actually use the equation. You can plug in those times and get it, or you can use the principle that it goes like the square of the time. So you just multiply the 1 second time by 4 for the 2 seconds, and you multiply the 1 second time by 9 for the 3 seconds, the 1 second time by 16 for 4 seconds, by 25 for 5, by 36 for 6, by 49 for 7, so on and so forth. Anybody have any questions on that? All right. Example 216 says, suppose the ball in example 215 is thrown downward with initial velocity of 3 meters per second instead of being dropped. What then would be its position after 1 second and after 2 seconds? What would its speed be after 1 second and 2 seconds? So that's just another example. In this case, they're wanting to know what would its position be. So you're going to use x equals 1 half at squared, but this time the v0t term is not going to be 0. So you're going to have to add that to it. That's for part A. For part B, what would be its speed after 1 second and 2 seconds? In that case, you're using v equals v0 plus at. Now, I didn't really have time to work that again, so I'm going to leave it at that. It's time for you guys to go. So thank you for coming, everyone. Make sure you chat me your first and last name. Also, make sure you turn in your syllabus cut and paste assignment because you're supposed to be dropped if you don't. And make sure you let me know about whether or not you can have your name or even occasionally your face appear on my YouTube channel. If you can't, I need to know that so I can make arrangements to not have that happen. So thanks for coming, everybody, and I will see you next time.
Thank you.
Thank you, Noah.
Thank you.
Thank you. I didn't see who that one was.
Colin.
Oh, okay. Thank you, Colin. I got 3 columns this semester. Big time. Anybody
I
have
had a
any
quick
questions?
question for you.
Yes,
Oh,
go
well,
ahead,
yeah,
Jaden.
I did.
No
All
problem.
right. Well, one, I do want to say I do really appreciate you breaking down the basics, all the way through.
No problem.
It's helping, knock off some of the rust from my high school physics class. But I do want to ask you, so I've been doing my homework on the using the e-textbook and all that other fun stuff.
Hmm.
Um, I despise how it's written, and I've been getting these low grades on my assignments because I'm taking hours to go through it to try to
Right.
figure it out, if that makes sense. So, what's your, I suppose your recommendation is more so what I'm asking you, because you make it so that the question is legible,
Right.
right? Instead of just sciencey mumbo jumbo, figure out the surface of the moon, right?
Right.
But
So, yeah, a big
yeah,
part, and let me first off warn you that at the end of this, I say warn you, I actually give you the advice that at the end of the semester, I'm going to give you an opportunity, and that means you, meaning everybody in the class, will have an opportunity to vastly improve their online homework score. So, because online homework systems are notoriously bad about having bad sig fig rules or making careless mistakes here and there and that sort of thing, I don't want my students trying to get the perfect 100. If they do, that's great, but I would say shoot for the 80, 85 range and don't beat yourself up if you can't do any better than that. And even as low as 70 would be fine because at the end of the semester, each student will have a wonderful opportunity that's not that hard to bring that score up from a 70 to a 100. So just
awesome.
know
I really
that.
do appreciate that because I was getting these 70s, and I understand that I have a bit rust, on my brain when it comes to physics. It's just I looked at that uh, textbook and I thought I had more rust than I gave myself credit for.
Well, at least you were awesome enough to actually reach a physics class while you were in high school. I never even got past chemistry and I failed that. So, you're way better off than many people. Don't worry about it. If the homework grade is dragging you down, don't worry. Around 2 weeks before the end of the semester, I'm going to give you a surefire way, and you meaning everybody, a surefire way to improve your homework score, and you will definitely be happy about it. So shoot for bare minimum 65 to 75. Because occasionally you're just not going to understand the topic very well, so you might not even get a passing grade on that, and you meaning a D or something. That's perfectly fine. But if you're shooting for an average of around 70 to 75, but you consistently can do well on the practice tests and the online tests and more specifically, the most important thing, the face-to-face tests. If you're doing that, your grade will just come out wonderfully. So don't beat yourself up
Awesome.
about that.
Okay. Yeah. I mean, I was, and I'm still gonna, put in as much effort as I can. It's just that was a huge concern,
Yeah, don't
and I
don't let
thought it
it
was a
depress
matter
you.
of not understanding the material because I go to my lab class and I understand it. I, listen to your Zooms and I understand it, and then I get on my homework assignment and I'm completely lost. Like I did the one of the estimation assignments and I genuinely had no clue I didn't even know where to plug in anything that you had said.
Gotcha.
And I thought that maybe I had a disconnect somewhere. So I
Well,
went
if
to
you
your
run into
YouTube channel and tried to
yeah.
figure myself out.
Well, if you run into anything like that, remember you can always take a photograph of the problem on your phone and then text it to me, and I'll give you some pointers. That'll get you out of the gate. Not only that, sometimes there's actually wrong answers in the online homework system. So you working really hard to get 100 sometimes is teaching you how to do the physics wrong. So I don't. That's why I don't want you guys fixating on trying to get a perfect 100. I want you to do enough where you feel like you've learned it so much that you can actually do well. And the best indicator is, can I get an 80 without looking up any problems on a practice test? So once you get your homework done, use that as the driving motivation. Can I get an 80 consistently on the practice test? If you are, then don't even worry about what your homework score is going to be because I'm going to give you an opportunity to improve it.
Thank you again. I appreciate it. You have a good evening.
You too, Jaden. Thanks for asking. Anybody else have any questions? Ryan or Melanie or Zach?
Yeah, I got a question.
Go for it.
So for the syllabus thing, I missed the beginning of the
Hmm.
class, but is it okay if I like filled out in pen and then uploaded file? I don't have PDF or
Yeah.
anything
So,
like that.
by the way, you do have it. All you have to do is call
Oh,
the
okay.
helpline through TCC. You get all the
Oh,
whole Microsoft suite for free.
oh,
But
nice.
yeah, you can take a picture of it and convert that to a PDF and upload it.
Okay. All right. And it's
There's
just the last page.
Yeah, you'll see there's like a bunch of equals, and it says begin, cut, and paste here, and then there's some
Oh, I
equals.
see.
So right in
Okay.
between those two equal symbols.
Okay. All
All right.
right. Thank you.
Thanks, Ryan.
No problem.
Hey, Melanie, you have any questions, ma'am?
Yeah, I did.
Okay.
When we were going over equation 6, I just had
Hmm.
a quick question because I think I got lost along the way there.
Okay.
Um, so because it said when we had got to the point of like x equals x naught and then
Uh-huh.
v squared minus 2v v naught,
Hmm.
and we were simplifying that equation, where did the last part, the minus 2v naught squared go?
Minus 2 v naught. Oh, okay. So the minus 2 v naught squared was being
Yeah.
subtracted from v naught squared. So it's like 1 v naught squared minus 2 v naught squared gives you negative v naught squared.
Oh, okay, there we go. I thought, okay, there we go. For some reason, I thought that the first Vnos squared stayed and then the second one was
Yeah.
just gone for no reason.
Yeah, it's
Okay.
the things that we think when we're doing arithmetic. It's just,
Yeah,
but I
okay.
feel you.
Because yeah, I've had problems with arithmetic in the past, so that's it. Okay, there we
Yep,
go.
me too.
Thank
I'm
you.
really horrible at it. So you're welcome, Melanie. Have a good one.
You too, thank you.
All right, it looks like, yep, that's it. I'm going to stop sharing and thanks everybody for coming. I hope this was all helpful. There's the last two pages, and hopefully I explained 216 well enough for y'all to get started on that. I think you're definitely in a good spot to complete this chapter. We'll cover some more examples next time. Have a good day. Bye bye.